Hi, my name is Fabian Kutschera and I want to present on linking dynamic earthquake rupture to tsunami modeling for the Reykjavík transform fault system in North Iceland. This research is part of the CHEESE project, which has the goal to establish a new center of excellence in the domain of solid earth. In most cases, tsunamis are associated with strong subduction zone earthquakes. So why do we consider a tsunami modeling for a transform fault system? As you might remember, a very powerful and very destructive, devastating tsunami hit Palu Bay in September 2018. And this tsunami was preceded by a moment magnitude 7.5 earthquake occurring on a strike-slip fault system, and was therefore quite unexpected. This picture shows the devastating impact, with houses completely destroyed and ships displaced on land. A study from Ulrich et al. Found out that co-seismic displacement caused by the earthquake may play an important role for the tsunami genesis. They used a physics-based approach and coupled the earthquake and tsunami modeling, and were therefore able to reproduce key earthquake characteristics as well as parts of the tsunami propagation, which you can see in the video on the right. This has, of course, important implications for tsunami modeling and strike slip and transform fault systems worldwide. Now, coming back to the Reykjavík fault, there hasn't been an earthquake with a magnitude stronger than 6 in more than 145 years. Besides, the strain accumulation on the locked HFF is equivalent to a potential moment magnitude 6.8 earthquake. Therefore, our goal is now to reassess the tsunami potential of the Reykjavík transform fault system. The HFF is about 100 kilometers long, with both right lateral faulting and normal movements, and connects the Mid-Atlantic Ridge with onshore fault systems of Iceland. The HFF itself is also partially located onshore, striking directly beneath the town of Reykjavík. Red lines in both figures represent proposed fault geometries, the complex fault geometry on the left and the simple one on the right. Yellow circles indicate relocated seismicity with magnitudes stronger than 2 from 1993 until 2019. Blue stars on the left-hand figure show historic earthquakes, for example this magnitude 7 event in 1755, which might have also produced a tsunami according to local annals. And then there are two 6.5 events in 1872 on the HFF. On the right-hand side, you can see some of the towns, which are used later on for reassessing the tsunami potential. The picture on the left is from the Northquake 2019 workshop, showing the coastline and this dashed red line marking the HFF striking beneath the coast and Flatey Island. So which ingredients did we use now? We used bathymetry and topography of the area, a 3D velocity model from Abril et al., as well as newly inferred fault geometries, as you have seen on the previous slides. We then used the stress map Iceland from Ziegler et al., including primary stress orientations and the stress shape ratio constrained by the inversion of earthquake focal mechanisms. In the end, we apply a Tanioka filter by considering the contribution of the horizontal ground deformation to the vertical displacement. Our computational modeling is based on open source software. We simulate our dynamic earthquake rupture models with SciSol, which is one of the 10 solid earth flagship codes of the CHEESE project. SciSol can efficiently model spontaneous earthquake rupture across complex fault networks like we have it, including seismic wave propagation with high order accuracy in space and time. Thereby, it uses an arbitrary high order accurate derivative discontinuous Galerkin method with unstructured tetrahedral meshes. Samoa Flash is used for the tsunami simulations. It solves 2D depth integrated nonlinear shallow water equations, which are basically a simplification of the incompressible Navier-Stokes equation. Samoa Flash uses adaptive mesh refinement and applies Sierpinski space-filling curves to optimize the computational running time. Important to point out is that Samoa Flash uses the full spatio-temporal evolution of the seafloor displacement in the simulation, which was modeled before with SciSol. Now let's have a look at the hypercenter locations. We simulated 6 scenarios, 3 on the simple fault geometry and 3 on the complex fault geometry, which consists out of 55 fault segments in total. Our simulated magnitudes for the simple fault geometry are all around 7.3. And they are therefore stronger than the magnitudes associated with ruptures on the complex fault geometry, with the largest dynamic earthquake rupture being complex middle among the complex ones. The chosen hypercenter depth was 7 kilometers in all cases, which lies in between the estimated locking depth. What you're here going to see is how the dynamic rupture and the corresponding wave field for 2 examples propagate, on the left for the simple fault geometry and on the right for the complex one. The rupture nucleating in the east for the simple fault geometry propagates steadily to the west and over the entire main fault length. Rupture on the complex fault geometry, on the other hand, looks different. We can see several rupture jumps and renucleations of the rupture process itself. Besides, not every fault segment is activated. Rupture stops for complex middle at around 19 seconds and for simple east at around 25 seconds, while the wave field now continues to spread across the surface. Looking at the absolute fault slip underlines that the entire main fault length breaks in case of the simple fault geometry. We observe strong shallow slip up to 7.9 meters for simple east, and simple middle and simple west both also have strong shallow fault slip, even up to 10 meters, for example here at the eastern end, but since this part is already located onshore, this does not affect our tsunami genesis. And the absolute fault slip for all our dynamic earthquake ruptures on the complex fault geometries are smaller. Note here, by the way, the different scale, which is mainly due to the smaller moment magnitude of the models. And among complex west, complex middle, and complex east, we observe the highest absolute fault slip for complex middle with up to 5.2 meters. We defined the rake between 0 and 360 degrees, with 180 degrees indicating pure right lateral strike slip faulting. What we observe is a deviation from this pure strike slip faulting, and this rake deviation can especially be seen here, for example, for simple east near the surface. Kears and Aniko mentioned in their paper from 2020 that dynamic strike slip ruptures produce transient components of vertical slip near the free surface, which you can see when you look at the rake in our simulations. There are two aspects which are especially important to remember in this case, which Kears and Aniko point out. First, the confining stresses are lower near the surface than those at the seismogenic depth. And second, this effect of dynamic changes in co-seismic slip direction can be observed for surface breaking earthquakes. This slide shows the vertical displacement after the Tanioka filter has been applied. Yellow stars, by the way, mark the epicenter. Our dynamic earthquake rupture models reveal up to 1 meter of seafloor uplift for simple middle and simple east, and about 75 centimeters for simple west. A reason why the seafloor displacement is again smaller for simple west is because some of the maximum ground deformation occurs onshore. And I already want to point out that for simple east, we observe large seafloor displacement at the western end of the HFF, but less seafloor displacement within the bay of Reykjavík, which we can later see in the sea surface height over time plots. The complexity of the fault geometry is also reflected in the pattern of the ground displacement, which you can see, for example, here for complex middle. The maximum seafloor uplift for complex middle is about 0.5 meter. So we conclude that the vertical co-seismic seafloor displacement, in combination with a rake deviation from pure strike slip faulting, as well as this strong shallow slip near the surface, are now capable to generate a localized tsunami. What you can see here are the tsunami propagations based on the previously seen dynamic rupture model simple east and complex middle. We define the sea surface height as deviation from the mean sea level, which is around ±1 meter for simple east and ±40 centimeters for complex middle. And while we look at the tsunami propagation, I would like to point out again that we use the time-dependent seafloor displacements to initialize our bathymetry perturbations. In our simulation, we placed synthetic tide gauge stations in the vicinity of each town marked here. So Siglufjörður, Ólafsfjörður, Dalvík, Akureyri, Húsavík, and Grímsey Island. They record the arrival time of the waves as well as the maximum amplitude. We measure the sea surface height over time at each mentioned location for all 6 scenarios, but focus now on tsunamis with ruptures nucleating on the simple fault geometry. We can compare our results with some preliminary work done by Ruiz-Angelo et al., which was part of the Northquake workshop in 2019. They simulated a tsunami based on a uniform magnitude 7 strike slip event in the middle of the HFF and applied a simple Okada method, which represents a rather instantaneous sourcing of the tsunami given by static displacement, in contrast to our approach using the time-dependent seafloor displacements. You can see their hypocenter here in the middle, a snapshot of their tsunami on the right, and they also recorded the sea surface height at synthetic tide gauge stations. The similarity is that both their maximum crest of value difference and ours occurs at station Ólafsfjörður. Theirs is around 30 centimeters, while ours is around 90 centimeters. And the reason for the different values is likely the higher moment magnitude 7.3 in our models compared to 7 from theirs. And in almost all cases, our ruptures with hypercenter in the east cause the highest amplitude, except at station Húsavík. Here we observe SSH to be actually smallest, and we can explain this by recalling the corresponding distribution of the seafloor displacement, which was less significant within the Bay of Húsavík. For synthetic tsunami inundation and potential run-up, we consider Grimsey Island, the Bay with Húsavík, and Siglufjörður. On the left, you see the water height based on the bathymetry. Values on the X and Y axis can be understood as distances in meters. The figure on the right shows maximum inundation and run-up as a result of rupture on the simple fault geometry with hypercenter in the east. Blue colors represent the inundation depth, ranging in between 0 and 80 centimeters, and the red line marks the maximum run-up height. And at the end of this bay, so approximately here, there is a tiny airport located, which is by no means a touristic airport, but rather serves or has the purpose to ease medical access in case of an emergency. We observe now that synthetic flooding occurs now at this airport and also a bit further to the west, here, with highest inundation depth up to 60 and even 70 centimeters. Also, the town of Siglufjörður is not far away from where we observe maximum inundation and is partially affected by the tsunami, which you can see when you take a look at this red line, marking the maximum run-up height. We have now seen how dynamic earthquake rupture models can be linked with tsunami modeling for the HFF. However, dynamic rupture models can also be used for physics-based probabilistic seismic hazard assessment, short PSHA, which is a pilot demonstrator within the CHEESE project. Therefore, we choose again varying hypercenter locations to simulate different rupture scenarios to see how this affects the rupture dynamics and ground displacements or ground shakings. What you can see here are some examples of the simple fault geometry with hypercenter in the west, in the middle, in between middle and east, and at the eastern end of the fault. Our results show that all scenarios break the whole main fault length and generate similar magnitudes. Besides, the variation of the hypercenter location results in different rupture dynamics and slip distribution on the fault. For example, we have strong slip at the eastern end of the fault associated with rupture nucleating in the west, and vice versa for hypercenter in the east and strong slip at the western end of the fault. Besides, we observe nearly constant rupture velocity at the same depth when the rupture nucleates at one side of the fault. And depending on the hypercenter location relative to the geometry change, the rupture behaves different at the geometry complexity. Take model B5, here rupture breaks first to the east only and then bilaterally to both west and east. While for the other models, the rupture process is just smoothly and continues without any rupture delay. Our results show that physics-based ground motions are heterogeneously distributed along and across the fault. And even though the magnitudes of all four scenarios are almost the same, their ground shaking patterns differ from each other. And in addition to the attenuation when moving away from the fault, the ground shaking intensity is strongly affected by four factors. First, the geometry complexity of the fault, such as kinks or gaps. Then the rupture directivity, like the amplified ground motions in rupture forward direction. Third, the coupled effect of the fault geometry and rupture directivity, for example in figure E and figure F, showing intensified ground motion bands with an obtuse angle to the rupture direction at the geometry kinks. And fourth, the topography itself, since topographic features light up. We also compare the ground shakings with the ground motion models, short GMMs, which are derived by Kovsari et al. From seismic data in the tectonic and seismic symmetric southern Icelandic seismic zone, and they fit well with the GMMs. Another interesting effect is that even though the physics-based ground shaking patterns differ significantly, their average attenuation relationships are nearly identical, especially in the near fault region up to 20 kilometers. So, to wrap it up, I think first it should be mentioned that we can reproduce large historic magnitude rupture events by using geological and seismic data constrained models. We find out that a localized tsunami can be generated by vertical co-seismic seafloor displacement in combination with break rotation near the surface. We therefore conclude that the Húsavík-Flatey transom fault system in North Iceland has the potential to generate tsunamigenic earthquakes. We consider the rupture nucleation in the east on the simple fault geometry as worst case scenario, which results in up to 1 meter of crest-to-valley difference near Ólafsfjörður. Besides, we observe up to 70 centimeters maximum inundation near Siglufjörður, and we see that Siglufjörður is located within the potential run-up area. Thank you for your attention.